By 2026, Flutter powers nearly 30% of new free iOS apps. It's the primary engine for global cross-platform development. When developers finish a new app, standard practice dictates they run the source code through traditional security scanners before releasing it to the public. The scanner generates a clean report with zero findings. Yet once deployed, those applications often contain the exact critical flaws the tools claimed were non-existent. The tools the industry relies on to measure risk are structurally blind to modern cross-platform architectures. The disconnect starts with Flutter's ahead of time, or AOT, compiler. Standard security scanners look for vulnerabilities by tracing data flows through readable source code, shown here entering the compiler. But as it exits as a native ARM binary, the AOT compilation has completely flattened it. Function names and readable context are stripped away. Scanners evaluate the original Dart code to verify the developer's intent. Hackers ignore intent, may attack the compiled binary executing on the device. Testing only what the code was meant to do, rather than what the flattened binary actually does, leaves the real application completely unguarded. To understand the risk, we have to look at what actually happens when that binary reaches a user's phone. This shows an attacker using a standard tool like ATK tool to crack a compiled APK open. The process exposes internal resource files. From there, basic terminal commands sift through the decompiled output to extract hard-coded API keys or sensitive session tokens. Developers often run build flags to obfuscate their code, which scrambles class and function names. That forces an attacker to spend a few extra hours mapping the logic, but it does not stop the extraction. Flattening code is not the same as encrypting it. Assuming that compilation acts as a security shield guarantees your data will be exposed.
Even if a developer writes perfect code, they are still exposed to vulnerabilities buried deep inside the framework itself. Consider the 2026 exploit involving the cross-platform remote desktop app, RustDesk. This logic tree demonstrates the critical flaw. A maliciously crafted link targets the app's URI scheme handler, bypasses authorization checks, and permanently resets the user's password without asking for confirmation. Or take the recent memory corruption flaws discovered in libpng. Because that library is hard-coded into the Flutter engine's graphics stack to decode images, app developers couldn't patch it themselves. They had to wait for Google to release a core engine update. Your application's defense is strictly limited by the security of these deep underlying dependencies. Cybercrime groups have begun weaponizing the Flutter framework itself. They are using the platform's architecture to build backdoors like FlutterShell. The attackers package their malware as fully functional podcast players or PDF viewers. The apps work perfectly, allowing them to sail right through Apple's official notarization checks. Instead of hiding the virus in compiled code, the app uses a web view to pull commands from an external server across a bridge. It retrieves JSON instructions in real time, translating them to native shell commands running directly on the victim's machine. To avoid detection, the malware waits 10 to 20 minutes before ever connecting to the server, easily outlasting automated security sandboxes that only monitor apps for a brief window. The exact cross-platform flexibility that makes development so efficient now provides attackers with an undetectable mechanism for remote device control. Protecting a 2026 application requires a total move away from source code reliance. Engineering teams must stop assuming that clean code translates to a secure binary. The new standard is binary-first testing. Security teams evaluate the final compiled APK or IPA to monitor exactly how the application behaves while it runs. Client-side secrets have to be removed entirely, and sensitive session data must be routed into the device's AES-256 encrypted hardware key stores. This diagram shows Runtime Application Self-Protection, or RASP. It builds a protective perimeter around the live application, constantly monitoring the environment. If an attacker tries attaching a debugger, running an emulator, or injecting malicious code, the system immediately shuts down to protect user data. Writing secure Dart code is only the beginning. Defending your users requires fortifying the final compiled binary against the hostile environments where it actually lives.